everyone. Good morning, good evening, good afternoon. So I just wanted to kind of wrap up one of our conversations or kind of discuss one of these features that we didn't quite have time to get to on the last day we had class on Wednesday. So we finished up talking about the Coriolis effect. And I know I went through that a little bit quickly, so I would recommend giving the video that I have linked in the assignment a watch. It's a quick 3-minute video of National Geographic. They do like a really cool visual representation of the Coriolis force using the merry-go-round. So I think at the end of lecture, I kind of was able to at least kind of walk through a little bit that idea, but I definitely recommend giving that video a watch. And also, refer back to the slides in terms of Coriolis force rules, just kind of a little reminder that it deflects things to the right of the direction of motion in the northern hemisphere, to the left in the southern hemisphere. It's 0 at the equator and maximized at the poles. There's mathematical reason behind that. And then it only veers winds. It does not slow or accelerate winds. And then lastly, oh gosh, of course I can't remember the last one off the top of my head. But it's okay. I have it in these slides. But so those are the 4 rules. There will be a short answer question regarding them. Oh, I remember the 4th rule now. It's proportional to the wind speed. So if you're not moving or the wind's not moving, then there won't be any Coriolis acting on it. The faster the winds, the faster or the greater the Coriolis force. So that's why hurricanes have this really beautiful spin. That's why all these other large low pressure systems have a very, very distinct spin to them. So just kind of wrapping that part up there. If that concept is a little bit confusing, that's totally okay. It's definitely not going to be the last time we talk about Coriolis, because once we start talking about oceanic circulations, then we're going to talk about Coriolis again. So it's not the first nor the last time you'll hear about it. Anyway, going back to the idea of the global circulations, remember there were 3 circulation cells in each hemisphere. So we had the Hadley, the Ferrel, and the polar cells. So where the 2 Hadley cells meet, they converge. Remember that term, convergence, coming together. So when those 2 air masses come together from the northern and southern hemisphere, the air has to go somewhere, and it does not go down into the ocean or into the land. It is forced upwards. And if there's enough moisture in the atmosphere, once that upward vertical motion occurs and the air parcels expand and cool, then sometimes we can see those as clouds. So we're just going to go through a couple of examples of that. Here's like a little schematic showing the ITCZ, the Intertropical Convergence Zone. So on our left side here is the northern hemisphere, and on our right side is the southern hemisphere. So you can see in this very simplified schematic that we have our trade winds converging together, and then also allowing for some vertical motion here. And in this case, it was allowed to create clouds that are indeed raining. Just because it's cloudy does not mean that it's raining, right? So it's just a feature that we often see. And here's another way that we can visualize this using an infrared image of the world. We're looking at a full disk here, but mostly focused on the Pacific Ocean. So I will also mention that this feature is most predominantly visible over the Pacific Ocean because of the fact that the sun is directly overhead, which causes a lot of evaporation off of the oceans. So we see these cloudiness and potential thunderstorm activity from 2 things here, the convergence of the trade winds and the sun being directly overhead, which causes that evaporation and puts moisture into the atmosphere. So the way that I like to say it is that, every good outfit has an accessory. The Earth is no exception here, where the Earth has this beautiful belt of cloudy activity around the equator, roughly around the equator. And here's just another schematic to kind of show that, but I also like it because it includes the fact that at 30 degrees north and south, there tends to be a region of high pressure. So it includes on the bottom end of it, the northeasterly trades and the southeasterly trades as well. So just another sort of schematic form here. And then last thing is looking at the variation. So it does not stay in the same place all year round. Remember, we're a tilted planet, right? And so we have seasonal variation. So even though we say that the equator is like the middle of the Earth, there is still some variation in terms of solar angle, even at the equator. So that can help drive variations in the ITCZ. So what we're looking at here on the top side is the maximum for the northern hemisphere during their summer. And the bottom line is the maximum in the southern hemisphere during their summer. Some things to point out, and you probably kind of can see this already, is that there's a whole hell of a lot more variation over land. And when I mean variation, I mean more of like this sort of wavy pattern, right? So over the oceans, it's a little bit more straight in terms of what we visualize here, as opposed to kind of this wavy sort of pattern. And that's because there's no land getting in the way, right? Land is constantly getting in the way of atmospheric and oceanic circulation. This particular example is no deviation from that rule. So say if we were to be in the 90s film Waterworld, we would not see this variation over on the eastern side here. We would see it would just pretty, for all intents and purposes, be a complete straight line. Okay, so from here, what you're going to do is you're going to learn about what also comes forth when these variations occur in both the northern and the southern hemisphere, but we're going to focus on the northern hemisphere with something you may have heard of called monsoon climates. So be sure to check out the next few videos for that information. Thank you so much for watching.